quantum numbers describe values of conserved quantities in the dynamics of a quantum system. In the case of quantum numbers of electrons, they can be defined as the sets of numerical values which give acceptable solutions to the Schrödinger wave equation for the hydrogen atom. Perhaps the most important aspect of quantum mechanics is the quantization of observable quantities, since quantum numbers are discrete sets of integers or half-integers, although they could approach infinity in some cases. This is distinguished from classical mechanics where the values can range continuously. Quantum numbers often describe specifically the energy levels of electrons in atoms, but other possibilities include angular momentum, spin, etc. Any quantum system can have one or more quantum numbers. It is thus difficult to list all possible quantum numbers. How many quantum numbers? The question of how many quantum numbers are needed to describe any given system has no universal answer, hence for each system, one must find the answer for a full analysis of the system. A quantized system requires at least one quantum number. The dynamics of any quantum system are described by a quantum Hamiltonian, H. There is one quantum number of the system corresponding to the energy, that is, the eigenvalue of the Hamiltonian. There is also one quantum number for each operator O that commutes with the Hamiltonian. These are all the quantum numbers that the system can have. Note that the operators O defining the quantum numbers should be independent of each other. Often, there is more than one way to choose a set of independent operators. Consequently, in different situations different sets of quantum numbers may be used for the description of the same system. Spatial and angular momentum numbers. There are 4 quantum numbers which can describe the electron completely. Principal quantum number, azimuthal quantum number, magnetic quantum number, spin quantum number, traditional nomenclatures. Many different models have been proposed throughout the history of quantum mechanics, but the most prominent system of nomenclature spawned from the Hund-Mulliken molecular orbital theory of Friedrich Hund, Robert S. Mulliken, and contributions from Schrödinger, Slater and John Leonard Jones. This system of nomenclature incorporated Bohr energy levels, Hund-Mulliken orbital theory, and observations on electron spin based on spectroscopy and Hund's rules. This model describes electrons using 4 quantum numbers, n, a, ma, mis, given below. It is also the common nomenclature in the classical description of nuclear particle states. Molecular orbitals require different quantum numbers, because the Hamiltonian and its symmetries are quite different. Note that, since atoms and electrons are in a state of constant motion, there is no universal fixed value for ma and mis values. Therefore, the ma and mis values are defined somewhat arbitrarily. The only requirement is that the naming schematic used within a particular set of calculations or descriptions must be consistent. These rules are summarized as follows. Example, the quantum numbers used to refer to the outermost valence electrons of the carbon atom, which are located in the 2p atomic orbital, are n equals 2, a equals 1, ma equals 1, 0 or a 1, mis equals a 1/2. Results from spectroscopy indicated that up to 2 electrons can occupy a single orbital. However, 2 electrons can never have the same exact quantum state nor the same set of quantum numbers according to Hund's rules, which addresses the Pauli exclusion principle. A 4th quantum number with 2 possible values was added as an ad hoc assumption to resolve the conflict. This supposition could later be explained in detail by relativistic quantum mechanics and from the results of the renowned Sturmy-Gerlach experiment. Total angular momentum numbers, total momentum of a particle. When one takes the spin-orbit interaction into consideration, the L and S operators no longer commute with a Hamiltonian, and their eigenvalues therefore change over time. Thus another set of quantum numbers should be used. This set includes, for example, consider the following 8 states, defined by their quantum numbers. The quantum states in the system can be described as linear combination of these 8 states. However, in the presence of spin-orbit interaction, if one wants to describe the same system by 8 states which are eigenvectors of the Hamiltonian, we should consider the following 8 states. Nuclear angular momentum quantum numbers. In nuclei, the entire assembly of protons and neutrons has a resultant angular momentum due to the angular momenta of each nucleon, usually denoted I. If the total angular momentum of a neutron is Jn equals a plus s and for a proton is Jp equals a plus s, then the nuclear angular momentum quantum numbers I are given by I equals Jn a Jp, Jn a Jp plus 1, Jn a Jp plus 2. A 2, a 1, parity with a number I is used to label nuclear angular momentum states. Examples for some isotopes of hydrogen, carbon, and sodium are. The reason for the unusual fluctuations in I, even by differences of just one nucleon, are due to the odd-even numbers of protons and neutrons. Pairs of nucleons have a total angular momentum of 0, leaving an odd-even numbers of unpaired nucleons. The property of nuclear spin is an important factor for the operation of NMR spectroscopy in organic chemistry, and MRI in nuclear medicine, due to the nuclear magnetic moment interacting with an external magnetic field. Elementary particles. Elementary particles contain many quantum numbers which are usually said to be intrinsic to them. However, it should be understood that the elementary particles are quantum states of the standard model of particle physics, and hence the quantum numbers of these particles bear the same relation to the Hamiltonian of this model as the quantum numbers of the Bohr atom does to its Hamiltonian. In other words, each quantum number denotes a symmetry of the problem. It is more useful in quantum field theory to distinguish between space-time and internal symmetries. Typical quantum numbers related to space-time symmetries are spin, the parity, C parity and T parity. Typical internal symmetries are lepton number and baryon number or the electric charge. A minor but often confusing point is as follows: most conserved quantum numbers are additive, so in an elementary particle reaction, the sum of the quantum numbers should be the same before and after the reaction. However, some, usually called a parity, are multiplicative. That is, their product is conserved. All multiplicative quantum numbers belong to a symmetry in which applying the symmetry transformation twice is equivalent to doing nothing. These are all examples of an abstract group called Z2. See also: electron configuration, references and external links. General principles, Dirac, Paul A. M. Principles of Quantum Mechanics. Oxford University Press. ISBN A0-19-852011-5. Atomic Physics, Quantum Numbers for the Hydrogen Atom, Lecture Notes on Quantum Numbers, Particle Physics, Griffiths, David J. Introduction to Quantum Mechanics. Prentice Hall. ISBN A0-13-800-5326. Exer, Halson, Francis and Martin, Alan D. Quarks and Leptons, An Introductory Course in Modern Particle Physics. John Wiley and Sons. ISBN A0-471-88741-2. The Particle Data Group.